I thank the SPP for inviting me to speak here in the 38th SPP Physics Congress. Magandang umaga sa inyong lahat. Good morning. So the title is Need Connectivity, We Need Spectrum, Measuring Radio Frequency Spectrum Utilization in the Philippines. Okay. So, next slide. So when we talk about the internet, we're familiar with, of course, the utilization of this valuable resource. And when we connect to it, we use both wired and wireless infrastructure. So at some point, after we connect to when we connect to our access points through wireless waves, this router is connected to the internet via cables to a server, to a gateway somewhere. So it's a combination of wires and radio waves. Now, the wireless part of it, the wireless communication infrastructure, uses the radio frequency spectrum. And certainly this audience is familiar with the radio frequency spectrum, where we have compartmentalized this range of frequencies into bins, very low frequencies, medium frequencies, high frequencies, very high, ultra high, super high, extremely high, really very creative names. Of course, it's either between a few kilohertz to several hundred gigahertz, and then, of course, correspondingly in wavelength. We assign different applications to these frequency bins. And the reason for that is that in the beginning, we did not have the technology to access the very high frequencies. So we were confined to the lower frequencies in terms of our radios and televisions and communication systems. But increasingly, the higher range of the spectrum, the higher frequencies, the SHFs, the EHFs became accessible. Our electronics and the materials and the semiconductors that we use are able to operate at these higher frequencies, so hence they became more accessible. So by the way, as you know, the unit of frequency, which is hertz, is named after a physicist, Heinrich Rudolf Hertz, who famously said that, quote, "I do not think that the wireless waves I have discovered will have any practical application." Okay. So our civilization has utilized our spectrum by classifying these applications into the spectrum. And you see, I guess it's very hard to think of anything that is farther from the truth. And not only did Mr. Heinrich Hertz got it wrong, but he did not foresee how valuable the radio frequencies and spectrum would be. So this is really old data. This is 2003, but it shows how much spectrum is worth in the US compared to other things. Now, 17 years ago, the access to and the utilization of radio spectrum was equivalent to approximately $771 billion of economic value. This is according to the New America Foundation, the Citizen's Guide to the Airwaves. And why is it so valuable? Because the access to spectrum enables industries, enables a lot of downstream applications. You see how we have television, radio, the internet, depending on the radio spectrum. So spectrum is indeed a valuable resource, and the New York Times, in that several years ago, referred to radio frequency spectrum as the most valuable natural resource of the information age. Why is spectrum valuable? Because it is a vital part of the information or data superhighway. Your access to spectrum and how much spectrum you have leads to a determination of the capacity and speed, and also to some extent coverage that you will get as an end user. So if you have more spectrum, you have access to more spectrum, then you have more lanes. You have wider lanes. So you see how our communication systems have evolved from the first generation to fifth generation. With 1G, we had only analog voice communications. Really, it was not secure. It was really just used for talking. With the 2G systems like GSM, we now have a digital system where it's a bit more secure and encrypted, but it was confined to voice and SMS. And voice is a very narrow band application. It uses only a very narrow range of frequencies, a few hundred kilohertz. Well, actually, voice bandwidth is just 4 kilohertz, right? But because of redundancies in protecting the data and error correction, then it uses a slightly bigger bandwidth. But 2G still, no internet, our cell phones then had no cameras and not even browsers. Now with 3G, we had access to the internet on our mobile phones, and that continued to evolve with 4G and 5G through higher speeds, more capacity for consuming, creating, and sharing data. And you see this one on the right, you see with 4G, 5G, and with 4G and 5G, we're moving up to higher bands, 24 gigahertz to 40 gigahertz, as opposed to when we had 1G and 2G, we were in the lower bands, less than 1 gigahertz or around a few gigahertz. So we see that access to spectrum is facilitating these technology, a better access in terms of capacity, speed, and coverage. Now, in the Philippines, the agency responsible for regulating the spectrum is the National Telecommunications Commission. This is encapsulated or captured in a graphical pictorial form, as you see in front of you, the National Radio Frequency Allocation Charter Table. So whatever wireless device you're using right now, you can look for it in this table. Well, not the device per se, but rather the system or the application that it is part of, whether it is wireless local area networks or whether it is larger area networks or cellular and mobile. So from FM radio, TV broadcast, mobile cellular, Wi-Fi to satellite communication frequencies, it's all in here. So speaking of regulation, a responsive and effective regulation needs measurement. So we embarked on this project called Scalable Community Access Networks, in particular with this objective of measuring radio spectrum utilization at different locations in the Philippines in order to identify and quantify so-called white spaces. White spaces are loosely defined as unused or underutilized spectrum. And the goal, the overarching goal, is to illuminate the state of the internet infrastructure in the country and proactively find ways by which this current state may be improved. So you see here in the diagram on the lower left, you see the infrastructure that was built. This was by combined efforts of the University of the Philippines, the Advanced Science and Technology Institute, ASTI, in DOST, and also collaborators under a Philippines California Advanced Research Institute's project with University of California, Berkeley. So we've put up 3 tiers of measurement, a high-end system, which is really meant to have more in-depth, detailed, larger measurements. You see there a high-end system, which we could afford only to put in one place. A mid-range system, which we proliferate maybe to 5 places, that uses a software-defined radio that can measure these, acting as a signal and spectrum analyzer. And then a lower cost version, right there you see, which is more portable and is friendlier in terms of battery power, and you can put it on top of your vehicle. You see there in a car, actually there's an antenna there on the top. It should be not quite visible, but we also put it on boats, on these roll-on, roll-off ships that navigate the nautical highways in the Philippines to get an idea of spectrum utilization, not just on land, but also in maritime environments. We probably forget sometimes that we are an archipelago, and there were 70 million passengers on these ships in the Philippines in 2018 compared to around 40 million air passengers. So we need to get between our islands to go from one island to the other. We use boats most of the time. But then people spend a lot of time on these ships. What access to information do they have while they are on these ships? So these lower cost sensors are really meant for crowdsourcing measurements. You can use your mobile phone, but it is confined to the systems that are present on a mobile phone, whether it's 2G, 3G, 4G. It's not flexible enough to measure other frequencies. Okay. Next, so here is an example of such a measurement. We went to 3 places, for example, here, starting with Quezon City, and started measuring the spectrum. This is the TV band, TV frequencies. Ones used by TV broadcast for UHF. So you see there the utilization. The more red it is, that means it is more utilization. The deeper blue means there is lower signal or absence of signal. So that's an urban area. This is a suburban area, Dagupan City, Pangasinan, and then finally a rural area in Dilasag, Aurora, where you see deep blues everywhere. So you can eyeball a chart like this, and of course you can process it. So you start with a so-called spectrogram, and then you have this 2D plot. Then you maybe do some image processing on it, and then you can derive a more quantitative metric out of it by using formulas like calculating the channel occupancy rate by a max rule. This is Well, there are various papers that show us how to do this, and you can adopt those methodologies. So in the end, after applying these algorithms, you can end up with a picture that looks like this. So it is more easy to appreciate now the level of utilization of frequencies. And we can see they're literally white spaces. Those frequencies that have very low utilization or no utilization at all. That's what we call the white spaces. And white spaces are more prevalent, as we could expect, in rural areas compared to urban areas, because in rural areas, the population is sparse, and therefore corresponding investments in infrastructure are not made. But in the meantime, people live there. There are public schools there, there are hospitals there, and there are fishermen and farmers there who are not able to access information, as you can see now here. So what we say is the utilization of RF spectrum is a proxy indicator for connectivity. Okay, so we continue that. We made mobile measurements. We went from Batangas City to Calapan, and on a land trip to Rojas Port, and then to Caticlan, and then we spent some time in Boracay after that. So this is the land sea route if you want to go from Metro Manila to the famous Boracay Island, and measured spectrum along the way. And you can see here this narrative, this graphical narrative of starting from Quezon City, a lot of dark black spot that's really occupied spectrum. The y-axis here is frequency. This is as we move along. And then you can see as we're mobile, and then we reach Batangas City, you still see some stations there broadcasting. And then when we went on water from Batangas Port to Calapan Port, you see now signals disappearing. When we reach Calapan, the signals are restored. And then again, Calapan to Rojas, this is a really rural route, this one, rural areas, and you see there slightly more white spaces. And then we went to Rojas Port, a popular port because it's a destination for people, it's a stop for people going to Boracay. And then on water again, and then when we reach Caticlan, in Aklan, you see a few stations, but still largely a lot of white spaces. Okay. So that's the story of this measurement. So this spectrum sensing, we want to take it beyond occupancy of spectrum. We want to bring it into signal analysis. So what we say is that spectrum sensing evolves into a more general and comprehensive awareness providing mechanism. So by sensing spectrum and sensing signals, you can get context. Right? So this will, the current work is focused on advanced and multi-dimensional signal analysis. Advanced meaning in order to obtain better awareness, we move beyond energy detection using FFT algorithms and fixed thresholds by using, of course, adaptive thresholds, match filtering, cyclostationarity, and higher order statistics on the signal. Example of that would look like this. So you can infer information about modulation of a signal, the intelligence of the signal. And this is a commonly used technique. When we're trying to look for signals from outer space as well, we want to see if there's any intelligence, not just by the level of the signal, this occupying certain frequencies, but rather whether there is some modulation. Is there data rate? Is there some kind of pattern in the data? So you can infer those things by using higher order signal statistics and processing techniques. Now, another dimension, another component is going multidimensional. So to address future capacity requirements of communication systems, we exploit other degrees of freedom or dimensions other than frequency. So spatial domain, that means a spatial division, multiplexing, taking advantage of differences in polarization to convey different information at the same time, using, of course, time domain is there, and code domain. This is the so-called spectrum hyperspace. So, but in order to exploit these multiple dimensions, we need to be able to sense and measure them. So why do we measure spectrum? Spectrum utilization helps capture the state of connectivity. That is really, our thesis. And then it leads to spectrum policy reform, which can foster digital inclusion. In our country, we have many people left behind, and the state of the internet leaves much to be desired. We are not that connected. So according to our measurements, one specific result that we have been pushing is for portions of the UHF TV band, for example, 600 megahertz, which are unutilized or underutilized in rural areas. We would perhaps explore using these unused and underutilized frequencies to be reallocated for mobile cellular use on a selective regional basis, particularly in geographically isolated disadvantaged areas, or GIDAs. Specifically, we can create a new kind of entity, a new kind of service provider called community networks. These are people in communities that come together and fend for themselves. but they need to be enabled by technology. So we'll show that later. There are technology options for them that they can afford and they can deploy themselves. But also they need to be enabled by policy. They need to be enabled by spectrum, by having access to spectrum. So these community networks will offer data or internet service in these GDAS, but central to their operation is access to spectrum, or in particular to their own spectrum. So we're trying to look for spectrum for community networks, in other words. So community networks, what are they? It's an emerging model for communication networks where community members build and operate their own infrastructure, often not for commercial gain. This is helped along by increasing availability of affordable, readily deployable network equipment. Several examples around the world: Argentina, Brazil, India, Indonesia, Mexico, Peru, South Africa, Uganda, and the Philippines. Until about a year ago, we had a project on Tikari village base stations, and this is how it looked like. In Aurora province, deployed, I think, a handful, about six of these towers, which were, I call them community, quote, because it was really not initiated by the community. It was initiated by a project, and it had the support of one telco to allow them to use the frequency that they currently hold. What frequency did they use for GSM service in this area? It was a frequency held by one of the telcos, and they negotiated with them to use those frequencies. So they did not have their own spectrum yet. So this is an interim measure, really, in these areas to provide connectivity, so that when the community now, the standard of living improves, then people become more productive, and then regular infrastructure can come in. We've also utilized these white spaces and to relay networks using repurposed weather stations in the open sea. These meteorological buoys can be used as communication relays, and this had been tested on the field as well. So it's another way of bridging these remote coastal communities. Okay. So before we only had GSM base stations, voice and SMS, but we've upgraded that now. We have an implementation of an LTE base station. You see that there in the picture on the left, and being tested inside a Faraday cage and anechoic chamber. And we call it Locality. It's a 600 megahertz band 71 LTE base station prototype. So we wrote about it. This paper is going to come out in a couple of weeks. The Locality base station prototype is intended as a technology demonstrator to support spectrum regulation policy reform, enabling community networks. Now, we want to also measure the spectrum from space. So we proposed the spectrum monitoring from space with ICEP. ICEP is an external exposed deck in the International Space Station that can accommodate certain payloads. So the idea is, as the ISS passes overhead, we have our payload on the outdoor deck, and it can measure leakage signals from transmitters on Earth. And then we store that data, and then we download that data, and then we can share that data, not just with our countrymen, but with the entire world. So in the end, this is the concept of this payload. It's really a high-tech spectrum analyzer, broadband spectrum analyzer with a fancy antenna and a low noise amplifier. And of course, it has a GPS. So we want to mount it on the ISS. And the output of this would look something like this. It's some kind of a heat map showing where the radio signals are. And then you can overlay night lights in this area, so you have an idea of electrification plus connectivity. So the bottom line is we're trying to map the global digital divide from space and contribute this data towards a better understanding of addressing digital inclusion. To summarize, so this responsive and effective regulation of the RF spectrum requires measurement. Spectrum is a valuable resource of the information age. Measuring the utilization of RF spectrum yields proxy indicators for level and perhaps even quality of the connectivity, because the lower level of the signal in your area means you cannot really connect at high speeds. There is a fundamental trade-off there. And measurements are part of an information infrastructure that illuminates the state of the information infrastructure. And spectrum sensing should evolve to a more general and comprehensive awareness providing mechanism. And finally, some specific points. We are proposing a selective regional repurposing of 600 megahertz band for use by mobile broadband. So we want to allocate them to community networks. In this Locality, our prototype base station is a technology basis that supports the argument of repurposing this 600 megahertz spectrum for use by community networks. It's a reduction in capital and operating costs because it's based on low-cost commercial off-the-shelf hardware and open-source software. And this regulatory flexibility in non-traditional spectrum management in support of rural coverage, provides incentives for developing community networks in the country. So with that, thank you very much. Maraming salamat po.
I have very, very many happy memories of going to SPP when I was at NIP. And it's a pleasure to be back, even if it's a virtual visit. And today I'm happy to tell you about my work in biophysics, visualizing bending of RNA structures. I will start my talk like a biologist by first thanking all the people who made the work possible. My mentor and advisor, Lois Pollack, who is an excellent physicist and puts together this amazing team of people to work together. This work is done in her lab in collaboration with a very senior grad student, Yenlin Chen, who's graduating soon. And since we are physicists, we need the help of chemists when we do our work. Professor Scott Showalter and his group provided samples and helped with the measurements. And all the data, the X-ray data I'm presenting was taken at the Cornell High Energy Synchrotron Source. So I'm very fortunate to have in our campus synchrotron under our soccer field. The ring is here in the circle. And this is how Ithaca looks like right now. We are enjoying a very nice autumn season. My talk is about protein RNA interactions. We are a biophysics lab, and what we do is that we use the tools of physics to help biologists solve their problems. So my goal today is to tell you about the problems we're working on and how we want to visualize bending of RNA by a protein, and talk about our visualization techniques, small angle X-ray scattering and fluorescence resonance energy transfer. And the conclusion, spoiler alert, I want to show you that our protein of interest actually bends our RNA of interest by the end of the talk. So before I go to the problem, I just want to remind the physicists in the audience that in biophysics, we study the molecules of life, DNA, RNA, and proteins. And this is kind of like my physicist's version of the cell. The DNA is inside the nucleus, the RNA flits around, the protein is in the cytoplasm. Our lab is actually very interested right now in the biophysics of RNA molecules. We want to study microRNAs, which are functional RNA molecules that facilitate post-transcriptional regulation of gene expression. So essentially gene silencing. Again, physicists like this very, very simplified model, but in reality, life is messy. There are so many things going on inside the cell. Even just in gene silencing, there are so many components. And this is such a rich area of research. There's big potential in terms of learning basic biophysics. There's potential for therapeutics. In fact, this part of this diagram, RNA interference, has been awarded the Nobel Prize in 2006 in medicine. For the discovery of the small interfering RNA. And you might have heard the 2020 Nobel Prize in Chemistry is on another gene silencing mechanism, the CRISPR-Cas9. So all of this is, we don't have a lot of understanding yet. So there's so many open questions. And one of the open questions we're interested in our lab is how this primary microRNA gets processed by this protein DROSHA into a preliminary microRNA, and finally into this functional gene silencing RNAs. So we are going to zero in on this preliminary microRNA. We think they're very important to study because of the conformational dynamics involved. And we're looking at the interactions between primary microRNA and the proteins DROSHA and DGCR8. There is preliminary evidence that DGCR8 recognizes and possibly bends the primary microRNA, and then DROSHA cuts it. But we want to actually investigate the conformational dynamics of the bending of this RNA. And we do that using physics tools. So I want to introduce you to one of our tools, small angle X-ray scattering. I actually first learned of small angle X-ray scattering when I was an undergraduate at NIP. Dr. Banson was talking about his DNA experiments. So in SACS, we study the size and shape of freely diffusing biomolecules in solution. This is important for dynamics because the biomolecules are not trapped in crystal lattices. So SACS as a technique has been around for a long time. There's this very nice classic book that you can read if you're interested in the topic. But the field is ever growing just because there's a lot of improvements in X-ray physics, synchrotron beamlines, how the biomolecules are getting fabricated or getting better. And there's just a lot of open questions that can be answered using this method. In principle, it's really simple. The biomolecule is in this sample capillary. You shine X-rays on it and you collect the scattered X-rays in a 2D area detector. You convert it to intensity versus scattering angle or the scattering vector Q. So when we go to the synchrotron and bring our molecule, we get scattering profiles like this, which is intensity as a function of the scattering vector. But it's really hard to figure out what this means. But so we want to look at what they do by looking at the Fourier transform in real space. Again, I want to give a shout out to my undergraduate thesis advisor, Roland Sarmago, Dr. Sarmago, who first told me to inverse space, to how to Fourier transform things in my head. So if you look at this profile, you can actually see that this is a very distinct shape, the pair distance distribution function. It has a peak at 20 angstrom and a linearly decaying profile. So if you've looked at these images for a very long time, you tell yourself, that's not a circle, that's not a sphere, it is a cylinder. And it is a cylinder with a diameter of about 20 angstrom and a maximum dimension of 170 angstrom. So when we do the ab initio shape reconstructions of the primary microRNA, we were not surprised that it is looking like a cylindrical molecule. And this is the average reconstructed profile from the dummy atom reconstruction. We were able to dock our model, three-dimensional model in here. And basically it tells us that, oh, our RNA is kind of like a rod. It's a rigid cylinder. With that known, then we can go back to our biophysics problem. What happens when this rigid cylinder meets a protein? And we can come up with a physics hypothesis saying, oh, we think that the primary microRNA actually gets bent by this protein because it has these two sticky sides. But we need to prove it, okay? So we have an experiment, we go back to the synchrotron and we want to see if the RNA gets bent by the protein. But before we can see bending, we have to first prove that there is binding. So we look at the scattering profile of the RNA by itself and the protein by itself. This is in absolute units. And the RNA actually scatters more than the protein because it has a phosphate backbone. It's more electron dense. The scattering is dependent on the electron density and the shape factor. For a two-component system, if it's not interacting, we expect the scattering intensity amplitudes to be additive. But if so it should be just around 0.035 here if the protein does not bind the RNA. But for two systems that actually bind each other, we get a much higher amplitude because of the cross term, the interaction profile. But so we know that they're bound. We know that the amplitudes say they're bound, but it's really hard to model a complicated equation like this. So what we want to do is to make our problem simpler. And to do that, we want to add a contrast variation agent. In this case, we put our protein RNA complex in a sucrose solution, which dramatically changes the electron density of the solvent such that the electron density of the protein matches the electron density of the protein of the solvent, rendering it invisible. So we can only see the RNA. So here the protein is blank, and we know that the RNA in complex looks different than the RNA alone. We can go back to our pair distance distribution analysis, ab initio reconstructions, and we can see that yes, the pair distance distribution changes, our molecule seems to be bent, and we can go back, compare it with our 3D molecular dynamics model and starts bending it using this fraction of common contact algorithm. So is our hypothesis correct? Yes, we were able to show that the primary microRNA bends a unbinding DGCR8. It's really cool. We validated this using other model systems. We were just using a straight up RNA double helix and an engineered helix junction helix to show that, yes, when you have a bend, it really changes your P of R function. But since like biophysics experiments are always challenging and we need to convince our biologist friends that yes, it's bending, we have to look at another approach, this time using lasers and fluorophores to actually see bending in a different way. In this case, the RNA is labeled with 2 fluorophores. When the protein bends the RNA, it shifts our FRET signal to a higher FRET signal to show that the 2 fluorophores are coming together. This is my one slide on FRET. I just want to, hopefully, I have, in the time that I have been allotted, I was able to show you that we were able to use physics tools to solve a biology problem. And I was able to visualize bending of RNA by a protein. And this is really important because we think this bending of microRNA by DGCR8 could facilitate the cleavage. And you can imagine that the DGCR8 protein grabs the RNA, bends it, and then Drosha could come along and cleave it, and then you can release it, and then the next primary microRNA comes along. This has a lot of biological implications in recognition of molecules and processing efficiency. So this is my last slide, and I'm very happy to be back. Maraming salamat po sa pag-imbita.
Good day, I'm EJ Reyes from the National Institute of Physics. On behalf of my co-authors, Mr. Improso and Dr. Tapang, I will be presenting our paper entitled Comparison of Single Focus and Dual Foci Scanning in Single Photon Photopolymerization. In this study, a photolithography line scan of a single and dual focal scanner was simulated to compare their size output and pattern development, which will eventually be used for future system calibration and design. Before we proceed, let's talk about what photolithography is about. Photolithography is a transfer of patterns to photosensitive material, such as a photoresist, to create micrometer to nanometer size structures. One setup that is capable of doing such task is a direct laser writing setup, wherein light is focused onto a photoresist and is partially manipulated to scan over the desired pattern. In this case, a single focus is scanned over the line using a galvanometer scanner or GALVA. There are instances where multiple focal scanners are used, usually to create repeating geometric or non-geometric patterns, both having their corresponding advantages and disadvantages. In an example where they use protein-based photoresist, more resilient and functional structures were formed. Now, regardless of whether we use a protein-based or non-protein-based photoresist, such as SU8, designing a system to create such structures requires the forecast of their development. Thus, in this paper, we simulate single and dual focal scanning setups that use SU8 as a photoresist. We keep track of their size growth and edge profile development for size output control and future system calibration and design. To achieve this task, we employ the following setup. The light field from a monochromatic light source is expanded and equally divided towards two galvanometer scanner arms. Light is deflected from each galva and passes through the 4F setups. Then, light from each arm is combined using another beam splitter. That light is focused onto the photoresist area using an objective lens. We assign the optical and transverse axis as Z and X respectively. In simulating the galva's deflection of light, we add a phase grating to the light before the 4F setups. Now, the light profile is obtained by considering the objective lens as a physical optical Fourier transform. Now, the light profile along the XY plane is propagated using the angular spectrum method to obtain the actual or XZ point spread function of the light. The point spread function will then be used in simulating the photopolymerization process. The process is modeled after Dill's photoresist model, wherein the initiation of the cross-linkages of the polymers due to the exposure of light corresponds to a decrease in the concentration of the photoresist, specifically its photoinitiator. The photoresist layer on top of the substrate is divided into sublayers along the optical axis. In this model, the concentration of the photoinitiator decreases proportionally to the absorbed light A, the point spread function H, and the optical sensitivity parameter C. Other Dill parameters that describe the inherent properties of the photoresist, the bleachable and non-bleachable parameters, affect the absorbed light of the photoresist. To determine the formation of structures, a unit structure which is sampled similarly to the point spread function is formed when its concentration is less than the initial, which was set to 1. In this study, we simulated the photopolymerization of 3 cases: a single stationary focal scanner, and the 2.4 micrometer line scans of a single and dual focal scanner. In a single focal scanner, the two foci scan in similar directions, while a dual focal scanner scans in opposite directions, overlapping at some point. The simulation of the single stationary focal scanner or non-moving focus was done to establish the baseline size growth and profile development. This was also used to analyze the results of the line scan. It can be seen that the actual window was saturated during the whole exposure time, which shows how most of the energy is distributed along the optical axis. Furthermore, the ladder-like behavior was observed for size growth. This meant that the system is resolution limited, as seen in previous studies. This is more apparent in the changes in size of the structures. We see in the changes in size of structures that the local maxima, as seen as or peaks, reflect rapid size increases that could lead to unwanted structures such as disconnected lobes, seen in this figure. Meanwhile, frequently occurring peaks meant consistent and or gradual changes, which could be essential for size control. Now that we've established these characteristics, we proceed to the line scans. For a 2.4 micrometer line scan, it was seen that the single focal scanner can photopolymerize faster along the x-axis. If we use this 2 micrometer marker, we can see that the dual scanner has more gradual changes in size, which meant more control over the size output if there is a target size below the 2.4 micrometer scan limit. Meanwhile, it was seen that yet again the single focal scanner photopolymerizes faster along the z-axis, but not as significant in the x-axis. We can summarize their output speeds in this table. We observe 100 micrometers per second and 30 micrometers per second difference along the x and z axis respectively. Along the x-axis, the difference is significant considering that the typical DLW speeds are around 100 micrometers per second. Associating these output speeds with the edge profiles, we see that the single focal scanner produced smoother edge profiles compared to the dual's expected fringe surfaces. To summarize, a single focal scanner is capable of faster photopolymerization and smoother edge profile outputs, while a dual focal scanner has fringe surfaces but allows for more size output control along the x-axis. It's important to note that the simulations are known to be limited by the Fourier transform-based methods, maximum spatial frequency, and that the angular spectrum is inaccurate or known to be inaccurate for higher NA objectives. It is recommended to use vectorial-based diffraction to solve those limitations and to obtain the parameters of the photoresist and the galvanometer servomotor and PID control. Lastly, we would like to thank the Instrumentation Physics Laboratory from NIP and STAMP project under the DOST. Thank you for listening and have a nice day.
Good morning, everyone. I'm Kenneth Domingo, and I'll be presenting this paper on behalf of my co-author, Dr. Maricor Soriano, entitled Compressively Sampled Speech, How Good is the Recovery? So for the abstract, I'll be going through the keywords and I'll be explaining them as we go throughout the presentation. So modern signal acquisition technologies are mostly based on the Nyquist-Shannon sampling theorem. But in this paper, we want to use an alternative sampling theorem known as compressed sensing. Current literature focus more on generating computationally efficient algorithms or methods which improve the reconstruction quality. In this paper, we evaluate the reconstruction quality of compressively sampled speech using perceptually intuitive metric, specifically perceptual evaluation of speech quality, or the PESC as we call it. And we also use this side by side with the standard metric used in speech applications, which is the average segmental signal to noise ratio. And the main finding of this paper is that given all the parameters used to arrive at the reconstructed signal, the reconstruction quality in terms of PES can be described solely by the
Excuse me,
compression ratio.
Kenneth.
Yes.
There's a static in your audio signal. Perhaps you need to stabilize the connection.
Sorry,
Thank you.
I think it's the fan. Okay. Okay, so for a quick overview of Nyquist-Shannon sampling, given an incident signal which is continuous, we can describe this by its highest frequency or bandwidth frequency f sub b. And via sampling, we take snapshots at fixed intervals in order to obtain this discrete representation of the signal and then reconstruct the original signal via interpolation. And then for a signal with multiple frequencies, you might ask how far apart should those time intervals be? Nyquist-Shannon tells us that you should sample the signal at a rate that is greater than twice the signal's highest frequency. In contrast, compressive sampling, given the same signal, you sample it at random points in time and with less samples that would be required by Nyquist-Shannon theorem. And we perform minimization in order to reconstruct the signal. So to contextualize the objectives of this paper, previously we presented compressive sensing of a recorded guitar signal just playing one note. And we were focused only on recovering the frequencies involved. So we ignored the magnitude and we also compared common minimization algorithms used in compressed sensing. For this paper, we are interested in performing compressive sampling on speech, factoring in both magnitude and frequency in error evaluation, and quantifying signal reconstruction error with perceptually intuitive metrics. The dataset that we used is obtained from a publicly available version of the TIMIT continuous speech corpus. The original dataset contains over 6,000 speech recordings, all having the same format and sampling rate, and they are composed of sentences contributed from different research institutes. Our methodology consists of the following steps. First is the pre-processing.
Kenneth,
It's
excuse
only
me.
one step
Sorry,
since the range of
Kenneth. The mic, can you put it? Can you
yes.
lower the transducer, the mic a little lower so it will not be directly to your mouth? Let's try. Thank you.
Okay. Hello, is this better? Oh, sorry. Okay, so since the range of human speech is not as wide as that of human hearing, we can safely downsample the signal to 8 kilohertz without losing any essential information. After that, we perform sparse transformation by converting it to the modulation domain. So we divide the signal into fixed frames, which where adjacent frames overlap window them, and then take its Fourier transform to obtain the spectrogram. For the reconstruction, we use the metric, the perceptual evaluation of speech quality. It's a prediction model that predicts how users would subjectively rate a signal from 1 to 5. But this algorithm is quite complex, so we refer to the PESC manual for a more detailed overview. The PESC value gives you a continuous value from 1 to 5, but we have attached qualitative descriptions for the integer values. And we also use the segmental signal to noise ratio. We just obtain the signal to noise ratio for each frame and average it over the whole signal. For the results, this is a representative case. We use this specific entry from the dataset. And for the parameters, we divided the signal into 1024 frames, where adjacent frames overlap by 75%. And we compress it by 40% from what would be usually needed from Nyquist-Shannon theorem. And for the minimization algorithm, we use lasso. So this is the data that we used. On the left side, we have the original signal, and on the right, we have the reconstructed signal from 40% compression using compressed sampling. Here's what the original sounds like. And then the reconstructed one sounds like this. So evaluating the metrics for this, we obtain a PESC of 2.5 and an SNR of 0.07. At first glance, you can't really tell how this sounds like without listening to the actual signal based on the SNR. But if you look at the PESC, provided the table that I showed earlier, we can tell that the reconstruction quality is slightly below average. Next, we are interested in how the metrics behave with respect to the parameters, specifically the compression ratio and the number of frames. So we vary the compression ratio in the range 0.1 to 0.9 in steps of 0.1. The number of frames, we vary them in steps of powers of 2, and the frame overlap constant at 75% in order to obtain the following error maps. So on the left side, we see that the PESC, as a function of compression ratio and number of subbands, we can see that the PESC does not have that much variation with respect to the number of subbands, but rather it is more dependent on the compression ratio used. The signal to noise ratio, on the other hand, is more dependent on the number of subbands. And from this, we can conclude that the evaluation of a perceptually intuitive metric, such as the PESC, is sensitive to changes in compression, while the SNR as a statistical metric, is more sensitive to the number of frames. And then finally, to answer the question, how good is the recovery, we can say that it depends only on the compression ratio that you use to sample the signal. Here are our references, and thank you.
Good day, everyone. I am Nonyal Paul Novabos from the National Institute of Physics, UP Diliman. I am part of Project Optical, or Optical Payload Technology, In-Depth Knowledge Acquisition and Localization of the Stamina for Space program. And with my colleagues, Jolie Charles Badalibay, Paul Leonard Acho Hilario, and Maricor Soriano, we present to you a motion-free push-rule scanner testing platform. A brief introduction on the Stamina for Space program. It is a DOST-funded program implemented by UP Diliman and DOST Advanced Science and Technology Institute. The program aims to build up the research and capacity-building activities on the satellite development and operation from its predecessor, the PhilMicrosat program. The PhilMicrosat program launched the Philippine satellites, namely Diwata-1, Diwata-2, and Maya-1 satellites. Stamina for Space also manages the operations of these satellites as developing remote sensing products. Project Optical is one of the component projects of Stamina for Space. We are currently building two types of payloads. The first one is HIPI, an airborne hyperspectral camera. It will take aerial images while mounted on a drone or a plane. And the next one is a spaceborne payload we call Malikmata. It will be launched on a satellite to take Earth observation images from space while orbiting Earth. One of the applications of these payloads is in remote sensing, which gives us a capability to survey a large area in just a small amount of time. Remote sensing has many applications, and one of them is disaster assessment, like the image on your right of the Taal volcano during its eruption back in January 2020. The image shows the surrounding area to see how much damage the ashfall has done. Another application is for agriculture, wherein we can assess the crops or vegetation's health using its spectral information. For imaging systems, when the relative motion of the camera and the target object is high, like a satellite orbiting Earth, scanning cameras are used. One type of such cameras are the push-broom scanners. Much like the sensor on your typical flatbed scanners, the camera is mounted on a moving vehicle, or in our case, a satellite, wherein it will capture the scene line by line to form a 2D image. One challenge in developing push-broom cameras is testing. The typical way of testing such cameras is to mount them on a linearly moving mechanical system, like the one you see on your screens. This emulates the motion as if it's mounted on a drone or a satellite. But developing this mechanical system can be a challenge in itself. In testing the functionality of the push-broom camera, the observer is scanning a stationary scene at a certain velocity. This gives us a relative velocity of the scene with respect to the observer, or VSO, equal to negative V. For our proposed functionality testing method, we instead move the scene, or in our case, the test image, across the stationary camera, but in the opposite direction. This gives us the same relative velocity as if we are moving the camera across the scene. And to implement this testing method, we'll only need a projector and a focusing lens to focus closer than the projector's closest focal point to project a test image onto the linear CCD sensor. This is a simpler way of testing as it eliminates the need of complex mechanical systems and just use a projector and a lens. It is more flexible as we can vary the viewing conditions of the test scene, like the scanning speed, resolution, and other parameters. It is cheaper since we'll only need a commercial off-the-shelf projector and a simplex lens. The experiment setup on the lower left shows the projector with the focusing lens projecting a diagonal line image onto the linear CCD sensor. For the actual test image, we used an undersampled Lena image as shown on the upper left. We used a presentation software to scroll the image downward frame by frame on the linear CCD. We then used an oscilloscope to capture and digitize the analog signal from the CCD, then transfer the data to a computer wherein we process the data using Visual Basic and render the image. The experiment resulted into this final rendered image. Only 50 lines were captured for this experiment, so the image looks pixelated. However, this serves as proof that the linear CCD sensor can indeed capture an image. And to assess how the rendered image compared to the original test image, we used Linfoot's criteria of merit given by the equations on the left. F is for fidelity, Q is for the correlation quality, and C is for the structural content of the image. They are computed based on T, or the overall shape of the target, and I for the resulting image. And the M and N are the rows and columns of the image. So for an ideal imaging system, F, Q, and C will have a value of 1. But for the rendered image, we got these values. This gives us a high value for fidelity, while a slightly lower values for Q and C could mean distortion and misalignments of the optical axis of the lenses. In summary, a simpler, more flexible, and cheaper way of testing push-broom cameras was presented. The setup used a commercially off-the-shelf projector and a single focusing lens to project a moving image across the stationary CCD sensor, and the experiment results showed that the linear CCD was able to capture the test image with high fidelity, but with slight distortion and tilt. Before I end my presentation, we would also like to acknowledge the Department of Science and Technology grants in aid for funding the Stamina for Space program. That ends my presentation. Thank you for listening.
Good morning, everyone. I'm Renal Principe Jr., and this is our paper entitled Color Error Tendencies in Spectral Super Resolution. This was done in partnership with Dr. Marcor and Soriano, and we're from the National Institute of Physics, UP Diliman. What is super resolution? It can be categorized into two, the spatial and spectral. For the spatial super resolution, we're trying to recover a high definition image from a low definition one. On spectral super resolution, we try to recover the hyperspectral image cube from a 3-channel RGB image. A brief background on color rendition theory. Color is trinity. It is a product of your reflectance spectra, emittance spectra of the illuminant, and center spectral sensitivity. The area under the curve of these products are your RGB digital counts. Why are we trying to recover the reflectance spectrum? It is because it is the spectral signature of your object. On specific bands, as you can see, you can extract certain regions or objects of interest, and this can help facilitate tasks such as segmentation, tracking, and automation. Currently, our hyperspectral imaging acquisition systems are push-broom linear scanners, LCTF, and spectral filter arrays. The problem is that they're all expensive, bulky, and requires long integration times. In this paper, we'll try to explore a mapping technique that's solely based on your RGB inputs. For relevant studies back in 2016, Dong et al. Used convolutional neural networks to facilitate spatial super-resolution. CNN was adopted by Galliani et al. On their paper called Learn Spectral Super-Resolution, and a year after, these methods have been benchmarked in an annual super-resolution contest named Entire Challenge. What we observe is that the problem is these computer scientists failed to check if their reconstructed spectra is physically plausible. It is because they only employed spectral metrics. Hence, part of our objectives is to emphasize the need for colorimetric evaluation in SSR research. As an alternative to CNN, we aim to solve SSR using a shallow neural network only. And later on, we aim to correlate the results based on input pixels chromaticity in a problem called color error tendencies. For the methodology, we designed a multi-layer perceptron which takes in 3 inputs that corresponds to your RGB and outputs 31 channels from 400 to 700 nanometers in 10 nanometers increment. We created 4 model versions by varying the number of nodes in the hidden layers. We trained it using the augmented Munsell and Sum and tested it using the Greta-Macbeth reflectance database. To explore the robustness of our architecture, we tested it on Cave dataset containing 32 RGB to hyperspectral pairs. On training, we used Keras and TensorFlow and employed sigmoidal activation functions on all the nodes. We also employed 80 to 20% validation on training split. And the results of the training is shown here. As you can see, models 3 and 4 yielded the lowest training and validation RMSE. However, model 4 trained around 3 times lower than model 3. For testing, we employ these metrics. RMSE measures the residual error for each band, while SAM resolves the spectral shape similarity of the reconstructed band and the actual band. For the color error metrics, it measures the Euclidean distance between the transformed, recovered, and actual spectra in CIE-LAB uniform color space, that's denoted by delta E76, CIE-LCH cylindrical color space, delta E94, and lastly CIE-LUV color space, delta E-LUV, which deals with the additive mixture of colored lights in computer screens for graphical applications. For the results of our Macbeth, we've shown here the results using Model 3, where your actual spectra is denoted by the red broken line and the predicted spectra is denoted by your blue broken line. We render the colors for qualitative comparison. On the left side is the actual and on the right side is the predicted. And we put a quantitative measure delta E76 on each subplot. It turns out that different colors tend to have different levels of colorimetric error. Now, averaging the results for each model, it was observed that models 3 and 4 perform closely in terms of the mean value as per the box plots. This is also true for the colorimetric error. And in conclusion, for our Macbeth results, Model 3 is the optimal model given its relatively lower training, validation, and testing reconstruction errors, plus faster implementation time in comparison to Model 4. Looking closely on the renditions, it was observed that despite having low RMSE, Some patches rendered colors that are very perceptually different from their original color. This can be seen as the delta E greater than 10. This motivated us to explore how error-prone certain colors are. But first, we employed our architecture on cave dataset containing 32 RGB images of challenging objects, and each RGB image will have 31 hyperspectral channels. A sample prediction using our model tree, the architecture can qualitatively represent the hyperspectral image cubes of the cave dataset. Band response shows segmentation capabilities, and the rendered RGB image appears similar to the input RGB image. But our interest is to utilize the abundance of the RGB data for cave dataset to quantify color error tendencies. What is color error tendency? It is the error likelihood given an input pixel's chromaticity, where negative A and positive A denotes the greenness and redness, while negative B and positive B denotes the pixel's blueness or yellowness. Since our input is RGB, we can transform that into chromaticity A and B coordinates and associate the errors that we obtain from that. So this is the process of extracting the color error tendency. We try to remove the influence of the a priori probability by stacking and averaging the cumulative value. As we can see, RMSE turned out to be higher on certain regions in the chromaticity space, as seen by the swelling on the Hall's parameter. So this denotes that in this area of chromaticities, we'll have higher RMSE. Now doing this for all of our metrics, RMSE, SAM, and color error metrics, our error tendency plots revealed that the greenish pixels of the cave dataset are error prone. But looking closely, RMSE is higher for a wide range of values, that is for yellow-green up to the blue-green colors, while colorimetric errors had islands of low errors on the second and fourth quadrants. Hence, good RMSE does not necessarily mean good color rendition, and it can be shown by the non-correspondence of our spectral metrics and our color error metrics. In conclusion, we swayed away from the trendy deep learning approach and showed that a simple neural network can facilitate SSR. We did this on Macbeth and the cave dataset. Also, we supplemented standard SSR spectral metrics with perceptual color errors, which we observed that there are instances of low RMSE and it rendered perceptually different from their original colors. Lastly, color error tendencies based on pixel chromaticity revealed the non-correlation of the spectral and color errors, hence reinforcing the need for colorimetric evaluation on future SSR research. I'd like to acknowledge DOST-SEI for funding my thesis, on-the-job training, and for my scholarship. And these are the references for my paper. Thank you for listening.